Well, hi all. So this is the first powered test of my big track system. This is only the 2/3 prototype. For those of you who saw the early view video, this is the 2/3 prototype. 2/3 meaning there's only 2 suspension systems, 2 trucks. The final track will be 3 of these, 1, 2, and a third one, so 12 wheels. So a bit longer, but this was a good place to stop because it's as complete as I can get it to do a powered test. And that's what I'm going to do here today. I am so excited. So not a lot of preamble. I'm going to just figure out how to clamp this to my table so that I can run it. And then I will show you the after I've had some time to play with it and run it and make sure everything's working right and had some fun. Then I'll take you through the electronics that I'll be using to control the whole system. And then we'll have a look at the gears and I'll show you how I made those, specifically focusing on the drive shaft, pardon me. And a little bit of engineering I did there to figure out how to get the power from the final gear to the drive cog. Pretty neat solution, I think. Then I'll talk about the suspension system and the trucks and how the bearings are built into there. And then we'll go up to the front and we'll look at the automatic track tensioning system. That's not complete, but I'll talk more about that later. I'm just really excited to get this thing going. I did some more tests up here with the track pads, which I'll talk about. Before we get started, I just need to tighten the things on my tripod. Sorry about that. If we just have a look over here on the computer, you should be able to see that window there, that application. So this is how I'll be controlling the app. Down here is the slider for throttle. I'll be using that one, and that's really it. The rest of it, don't worry too much about. That's for part of the different system. Okay, let's get this back. Sorry about that, but at least I got a tripod this time. Okay, so let's get this bolted or mounted or clamped to the table somehow, and I'll be back in a minute. Boy, I'm excited about this test. Alright, I think we are good to go. I hope that's a good view for the camera. Hopefully there's some light on it. How's that? Okay, so you probably can't see what I'm doing up here. Well, maybe you can. Well, first let's plug the battery in. We got a flashing light. We got a flashing... Why isn't my green light flashing? Okay, let's connect. Failed to connect. Why? What came unplugged here? Alright, something came unplugged. Be back in a minute. Alright, I'm back. I found the problem. There was a loose wire. It was between the keyboard and the chair. So, I just simply forgot to set the baud rate when I was connecting through the program. I forgot to set the baud rate for the communication. So, I think we're ready to go, ladies and gentlemen. This is the first power test of my big track system. I'm nervous. Okay, so first I'm going to power it up slowly up to 5%. My previous test of a prototype gearbox, it was just a gearbox, showed that the motor started spinning around 3%. So I'm going to slowly step it up to 5% and see what happens. 0.8, 1.5, 2.3, 3.1, 3.9, 4.7. So 5.5, there, 6.3%. I guess with the track on there, it's a little more resistance. So that is 6.29921% power. moving. It's doing its thing. Let's go up a bit. 7%. 7.8, 8.6, 9.4, 10.2%. %14.9%. %20.4%. %25.19%. You can't see my face, but I'm grinning like a bastard. That's 30.7%. This thing's gonna be fast. 35%. That's 40%. Oh yeah. Lots of torque. Lots of torque, baby. So that's 40.15%. That's 45%, and it's loud. %50 speed. We are at 50% speed. And I knew those gears were going to be loud, but holy crap. Okay, that's 60% speed. Boy, those gears are loud. That's 70% speed. 70. 75%. %80 speed. 85%. That's 90% full speed, 90%. Yeah, this thing's gonna be fast. That's 95%. 96. 97. 98. 99.2. 100% power. 100% power. Oh yeah, this thing's gonna be fast. This thing is gonna be fast. Holy crap, is that thing loud. Huh. That's loud. That's a lot louder than I was expecting. All the noise is from those gears. I wonder if I grease them, if that's going to help. Well, they don't feel warm at all, so that's good. I think I got a gear rubbing there, maybe. Oh well, that is a 100% successful test, ladies and gentlemen. So let's just jump this up to, I don't know. I'm going to jump this up. I'm going to do a standing start to about 35%, 40%. Standing start up to about 50%. I'll stop. Standing start up to about 70%. I'll stop. Whoa. Motor does have a slight warmth. It's obviously warmer than room temperature, but that's probably not a bad thing. Standing start to about 80%. Alright, let's put this puppy in reverse. Seems a little bumpier. Why is it? Is it losing track? What's going on here? A little bit of a... What shoes are those? It's those ones. Why? That's weird. Those shoes seem to be just a little wider for some reason. Well, it would be nice to figure out how to get the gears quieter. But otherwise, I couldn't be happier, baby. This is a... Oh, this is going to be a monster tank. Wow. Just wow. I am really happy with it. It's loud. Oh well. Wow. So I got a little bit of rub in here. I got a little bit of dust coming off under the wheel there from something rubbing. So one or two of those tracks, they seem to be just a little thick. Otherwise, everything seems to be holding up well. Okay, so I'm going to undo everything here. Sorry, I just had to play again. I'm going to undo everything, and then I'll come back and I'll talk about the control system, the gears, drive shaft, a few other bits. This thing is going to be fast. I wonder if I can count. Probably not. Maybe I can use the video and try and count how many times one of these goes by in a second. And then do some math. Figure it out. Maybe one of you guys watching could do that. If you know how, maybe you can time and count how many times one of these track pads was going by at full speed. And give me an idea of what its speed might be. One shoe is 34 millimeters wide. Here to here is 34 millimeters. Center to center, 34 millimeters. All right, I'll be back in a bit. All right, I'm back after that very successful test. Okay, so first of all, let's talk about the electronics and how I'm controlling the system. So over here, I've got the application on my PC. Hope you can see that. It might be a bit of an angle. This is written in C++ with the Qt framework. What this does is, it's going to be doing a lot more than I'm going to tell you right now. But suffice it to say, this side is what's controlling the motor right now with the sliders. So this app opens up a serial port to this thing. You can see it's actually just plugged in via USB. This is a 915 megahertz radio RF transceiver. For those of you who might recognize it, you can buy these off of Hobby King for really inexpensive. They're fantastic. I use them on my quadcopters. You get about 1 kilometer of range out of these things. What's really cool is their basic serial. These things have 2 ports on them. You got a USB port and then you got all those pins. I hope you can see that. So you plug it in to your serial or to your USB on your computer and it shows up just as a standard serial port. So you can open it just like you would any serial port and send serial data to it just like you would any serial port. On the other side of the coin, let's make sure I got this lined up correctly, is all of this stuff right here. Just prototyped right now. So this is the other transceiver. Now when you buy these off of Hobby King, they come with this wiring harness. I hope you can see that. All you got to do is cut the basic end off. It comes with a mini connector. Cut it off, put on a standard pin header, and written right on the case You got 5 volt receive, transmit, your CTS and RTS lines, and ground. So the CTS and RTS aren't actually part of the basic high wiring harness, but the pins are there, so you can just make yourself a new header if you wanted to use them. Otherwise, these run at 58,700 baud. So you just connect it to your Arduino through your standard wiring setup. Create a software serial object. You know, boom, 58.7 baud rate, 8N1, and you've got an RF link. Just that easy. These have built-in full duplexing. Send and receive simultaneously. It's awesome. So the program on the computer is communicating to this Arduino through the RF signal. It's beautiful. The Arduino is the main brain. It's taking all the data, parsing it a little bit, and sending it out to this thing. I hope you can see it. Let me just look at my camera. Yeah. This is the Sabertooth 2x12. It's made by a company called Dimension Engineering. I think you can even see it on there maybe. It says right back there. I don't know, you probably can't see it. Sabertooth 2x12. What that means is it can run 2 DC motors at 12 amps each. Peak up to 25 amp. These Sabertooths come in as a 2x5, so 2 motors, 5 amps, the 2x12, and the 2x25. So you want to run some big motors? There you go. What's really cool about this is, first of all, the package. It's all heatsink. So if you really are pumping out, 24 amps through this thing, 12 amps a channel, sufficient cooling, no problem. But what's really, really cool about it is the way you can interface with it. It has a whole variety of modes available. There's the dip switches right here you can see, and you can set a whole bunch of different modes. If you're really curious and you want to go into details, just Google it. It's a Sabertooth 2x12. Real quick though, you can interface through just basic analog signals. So on this side, you got this is a 5 volt out, 1 amp, 5 volts. So you can power your Arduino and a couple of servos all off of this thing. Your raw input is on this side. 5 volt and ground. This is S1 and S2. So S1 on an analog signal controls this controls motor 1. S2 controls motor 2. Just an analog signal. So 0 to 5 volts. 2.5 volts, or if you were using an Arduino, 127, 0 to 255. For 127 is neutral. 127 and up is forward. 127 to 0 is backwards. So 126 would be like just a little bit backwards all the way down to 0, which is full backwards. So that's one way you can control it. Another way you can control it is through RC receiver, through standard servo signals. And again, one servo signal into here, one into here. So you can actually plug this into your standard RC receiver that you normally have on a RC car or airplane and control motors with that signal. But it's got 2 other modes which are even more cool. It has a simple serial mode, which uses just one line. Using the serial mode, you're actually just using serial data, sending serial data to that, and controlling both motors at the same time. The more advanced mode is packetized serial communication, and that's the one I'm using. If you go to Dimension Engineering's website, they have an Arduino library that you can download, and it handles all of that packetized serial communication for you. This thing is so easy to use. You just simply connect your one pin, the yellow one output pin, or this one pin, to one pin on your Arduino, create a new software serial object. Because you're only using transmit here and receive here, when you create your serial object, you're actually going to use the not a pin macro for the receive pin, and then whatever pin you're connected to on here. So you create your software serial object, and then you create your Sabertooth object, and you pass it your software serial object. And now you have a Sabertooth object that basically has 2 functions, drive and turn. The reason is this has built-in differential steering. When you're using serial communication, built-in differential steering. So cool. Because when you're using a tracked vehicle, you've got 2 motors, left motor, right motor. When you want to turn, as you know, you change the speeds of the motors. You have to slow down your left motor to turn left, or you speed up your right motor to turn left. Now you can do all that yourself on an Arduino, but it actually gets kind of complicated when you're on the 0 point. the 0 point being neutral, or when you're at full speed, because you now have to figure out exactly how far you are on your motor scale, and then figure out which motor you need to speed up and which motor to slow down. So if you're at full speed, you can't speed up one motor to turn, you have to slow down the other motor. If you're at 50% speed, you want to slow one down, speed one up a little bit. If you're at 0, you're going to speed one up and put the other one in reverse and go backwards. The faster you turn, so if you're going to turn slowly, you'll just speed up the one motor, but if you want to turn quickly, then you speed up and slow down. It can get really complicated to handle a good differential steering. It does it all built in. I've done some testing with just 2 motors clamped to my table. This thing does really good differential steering, especially around the 0 point. It knows which ones to speed up, and then as you go faster, driving. It is so cool. So you have 2 function calls for your object. You've got ST drive, and positive numbers 0 to 1 or 1 to 127 is forward, -1 to -127 is backwards, and then you got ST or the turn, which is the same. Positive numbers turn right, negative numbers turn left. It's brilliant. But that's not all. This has lithium power cutoff on it. This has a whole memory, an EEPROM in it that you can actually program. You can change the baud rate. The default baud rate is 9600, so you can change the baud rate. You can change the LiPo battery. There's a whole bunch of functions. The LiPo battery saver means you set up a specific voltage, because you never want to run your LiPo batteries too flat, otherwise you have a problem. This will monitor the voltage and then automatically cut off when it hits that minimum voltage level, saving your LiPos. So you don't have to worry about, am I draining my battery? Do I have to check my battery? This will automatically cut off for you. This is a really great system, which is why they're not cheap. This thing is almost 100 bucks Canadian, but I love it. So there's my Arduino, my radio frequency transmitters, my C++ with the Qt framework, and oh yeah, that's it. Okay, I'll be back in a minute. I'm so excited and I'm yelling and you guys can't understand half of the crap I'm saying. I'm gonna go grab a drink. All right, let's talk about gears and motors. So I'm running these. These are from, you normally find these at a Traxxas T-Max or an E-Max. There's 2 of them. The standard and the reverse rotation. These are Titan Monster 550s. These are 21 turn, normally run at 14 volts. I'm just running them at 11.2 volts, whatever. A 3S LiPo battery pack. I could run them at 14 volts. I do have 5S or 4S battery packs. Huh. I just realized that. These are 14 volt motors. Huh. I might be getting more power, baby. Got an 18-tooth metal spur gear or metal pinion gear on these, and it's running on these 54-tooth spur gears. The reason why I got these spur gears is, I hope you can see that. There's these 3 holes out there around it that are 3mm holes. These are absolutely perfect for 3mm pan head screws. The pan head fits perfectly inside that outer ring. So the gears that I've printed are printed in ABS, and they look kind of like this. So if we can have a look at the system here, I don't know if you can actually see that very well. So this gear, these are printed in ABS. This gear is made with 3 holes in it, as well as it's got the center hole, which is a 3.3mm for a shaft. Then it's got the bigger hole on each end, and then it's got these holes around the outside with those. So these bolt right on to the spur gear using those 3 holes there. 3 30mm by 20mm screws, or is it 16mm screws? The nuts get recessed into here. The holes that you see on all these gears, these big holes, those are for bearings. If I take a bearing, they just get pressed right into these holes, just perfectly. They are a good press fit. I'm not going to push it in all the way. So when I put these on the shafts, there's a bearing on each side So these gears run completely on bearings. That hole on the inside is just a little bigger than this, so it's not rubbing against it at all. They run purely on bearings. All of the gears in here run on bearings. Full bearings. That's why I have so many damn bearings. I still got a lot of printing to do. So all of these are printed in ABS. You got the main spur gear. Couple of these. Whoops. I don't know if you guys can actually see or if I've got the light wrong or whatnot. So the main spur gear goes to one set of gears, and then to another set, to a third set, to the output gear. The final ratio is about 60 to 1. I kind of guessed on that, but I think I made a good guess. I think I've got a good power to torque ratio. This thing's got a ton of torque. I did a gearbox test, and I tried to hold the output shaft. I couldn't hold it. I really couldn't hold it at all. I could not stop that thing no matter what. Pardon me. So yeah, I think I've got a good... there's even the possibility that I might just rebuild the gears a little bit and change the ratio, maybe drop her down to like a 50 to 1 or a 45 to 1. Really increase the speed, depends. It's actually not going to be too hard because the way I've designed this, I can just design some new gears, keeping the same ratios. Well, the outer diameters. There's a little bit of gear magic, but you can actually change the gear ratio without having to change where your pins are. So that's the gears. All running on bearings. Lots of bearings. 3mm ID, 8mm OD, and 4mm thick. They're really awesome gears. I bought these at Solar Robotics for $1.35 each. I was going to buy them off of Tower Hobbies because all the bearings I've been getting so far are team associated bearings. They're listed as steering bearings, and you buy them in 4-packs, and they're kind of expensive. And I was going to go to Tower Hobbies to buy all the ones I needed. And it was going to come out to like $45 American. I ended up buying everything I need here in Canada for like $32. And they're good bearings. Okay, so that's the gears. But let's talk about the output gear, the final gear. So the final drive gear looks like this. Has this big hex in it. Why? So the drive shaft looks like this. And there's one of these. This is my torque collar. Inside here, I have another example I can show you from a previous print. This is what that plate here looks like that everything plugs into. You can see holes there for where the bearing shafts kind of are held in. This prints flat like this, and then I have a bearing mount with 4 holes that just screws onto this side and lines up those holes. So again, recessed everything. So inside here, I take one of these big ass bearings and it just presses right into this hole here. It is a tight fit. That time it just fell right in. So early prototype, not as tight of as a fit, but it just sits in there like that. But if you look at these shafts, they don't fit. Obviously, they're not the same size as the bearing. These are called FL 505s, or fiberglass tubes. Actually, there's 2 fiberglass tubes here. It's a 505 with a 414 inside it. The reason why I did that is to make these things really strong and really thick-walled. So the way I make these is I'll cut the 505 and the 414 to about that length, file the inside of the 505. They look like these. I normally use these for kites. This is the 505, this is the 414. I use these for big kites. If you file the inside of the tube, sand the outside of this until they have a really nice, perfect fit. And it's really easy to do. It doesn't take much work at all because the inside of the 505 is 414. So you're just filing the inside to get it clean, sanding the outside to get it clean. Epoxy the crap out of the inside of the 505. Epoxy the crap out of the outside of the 414. You want to make sure they got good coating. Slide them together, let it sit for 24 hours, and when it dries, you have a double thick-walled fiberglass tube. So this is just the end. If you cut this off, right, just even a millimeter in, you'll see that it is a perfect bond. There. So now you've got this double thick walled fiberglass tube. So once you've got the tube made, I take this is my torque collar. The reason why it looks like this is because this fits perfectly inside the bearing. It's a nice tight fit. That way there's no slop or anything. Oh great, there we go. I'll slide this onto the tube. This needs some filing on the inside because it's not a perfect fit off the printer. It's a little small. I do that intentionally so that I can file it, test fit it, file it, test fit it until it's an absolutely perfect fit. So I'll slide this onto the tube, and then I have a washer and a nut. Like you can see here, there's a washer and a nut. And I'll measure it to make sure that I have the right distance. And then, once this is on, I use this hole as a guide to drill straight through the tube, just like that. I'll take a piece of 3mm steel. These steel shafts, they come from Tamiya. These kits right here. They come from Tamiya, 3mm diameter shaft kits. They got hex, 150mm long hexes, rounds, and some threaded ones. I'm just using the hexes and the rounds, and they're beautiful. So once you got the hole drilled through the tube, you could take one of these, cut it to length, and it just drops right through. So now, this gets locked onto the fiberglass shaft with the pin. You then take your gear, the gear pops right onto here. It's a very tight fit, and in fact, I don't think these two are meant to mate with each other. I think these are older prints. So this one pops right on, actually. Just like that. You can see how it's a very tight fit. So now that pin is captured in there. Put the washer and the nut on. The nut cranks down onto the gear and it won't come off. And now, boom. When this turns, it turns the torque hex, which grips onto that pin, turns the whole shaft. The double thick walled, these things are very strong. These fiberglass tubes are ridiculously strong. I use these fiberglass tubes on 15-foot Delta kites, 12-foot Rokaku kites. You know, like big-ass kites that have a huge amount of pull. And I've never broken one of these 505s. They are ridiculously strong. And when you have the 414 epoxied inside with a double walled, that pin is not going to break this drive shaft. It is not going to torque all the way through. These gears will rip long before that happens. So once that's on there, remember this is sitting inside here, which is bolted onto here. And then it just fits. There's a slight raised bit on here. That rubs against the inside race. And if you were to look inside here, you can see there's a raised outside, which rests against the outside race so that you have good, proper bearing clearance. This fits right inside, and it just slides right inside that bearing. Really snug. I haven't really filed this one down, so there we go. I could push it all the way on, but I'm not going to. There is no slop in there, none at all. It is a tight ass fit. It's not going anywhere. It's beautiful. So the next step, great. There we go. I know I'm being long-winded about this, but I've had a few questions about how these drive shafts work, because it is a bit of a challenge getting a drive shaft, building a drive shaft. So now you've got this, it's pinned on, it's got a nut and a washer, you've got it on, you put this all the way through, right? You've got another bearing on this side. Now you take the other torque collar, which is thinner because the gear is thinner. You push this on, push it into the bearing, measure it so that you know how much you need to thread, and then you cut your threads. And I'm going to tell you right now, cutting the threads on here works great when you use a 1/2 x 20 thread. The die is a 1/2 x 20. If you accidentally do the 1/2 x 13, it doesn't work. The 1/2 x 20 is shallow enough that it actually doesn't cut all the way through the outside tube. So you still have fantastic bond between the outside and the inside. If you use the 1/2 x 12, 1/2 x 13 die, that cuts all the way through and into the inside, and it's actually kind of easy to strip the threads off. I screwed up and I had made this and I'd had it sitting around for a while, and I'd forgotten, wasn't paying attention. I put the 1/2 x 13 on there, cut the threads, and just destroyed it. The 1/2x13s work great. So like I was saying, you've got all this put together, right? It's on here. You've got it shoved through here. Now, you push this on into the bearing, measure where you need to cut the threads, take it all apart, cut the threads, put it all back together, put a washer and a nut on, crank it down tight. You're going to squeeze this right tight together. There's going to be no slop. It's going to be perfect. Once it's all tight together, take your drill right through the hole, cut the pin, drop the pin in, and then take the nut and washer off. And that pin's going to hold this beautifully snug up there. And you take the drive gear, put the drive gear over top of the torque hex, put your washer nut back on, snug it up. These, I used ABS to cut, to print the nuts. I used ABS because on these threads, you can get it really, really tight, and it behaves like its own stop nut, like its own lock nut. Those threads will actually sort of mush into the threads on here and will lock themselves tight. And you put a crescent wrench on here. This is just a little too big for a 3/4 inch wrench, I missed. You tighten that up, those are not coming off. They are a self-locking nut. So you put this back all together, crank it tight, and you're done. Beautiful tight fit. There's no slop, there's no play. You got the pins transferring the power. It looks good. So these will be cut off in the final track section. All this extra will be cut off, and then I'm going to put a cap on there. And these will look like cap nuts. In fact, I might even try doing a cap nut, but you can't tap into a cap nut. So that's why I'm going to do them in 2 pieces. But this will be a nice rounded nut on here, and it's going to look beautiful. So that's how the drive shafts work. I hope that was clear. I do realize that I kind of ramble a bit and I get off, but I'm excited about this. It is a really good system, and it works well for this scale. Now you can get the fiberglass tubes in smaller sizes, and you can always find ones that fit inside the other. If you're not sure where to go look at Goodwind kites. Just Google Goodwind kites. And then up in their top bar, they'll have the fiberglass and the carbon tubes. Go look at the fiberglass tubes and you'll see the different sizes. You can use this, use a smaller pin, use piano wire if you want to go really small, or you can go really big. You can get the fiberglass tubes up to like over 1 inch in diameter, so you can build giant ass shafts. You could actually like epoxy 3 tubes together to get really thick walled. Variety of options available. The thing about the threads, though, is that you need to have fine threads. You don't want to use normal or coarse threads. You got to be able to cut fine threads into this to get it to work right. So that is my gearing and drive shafts. And these bearings really aren't even expensive. If you're in Calgary and you're looking for bearings like this, go to Casterland. Google it. Casterland. They sell, when you walk in, you're going to see millions of different sizes and styles of casters and caster supplies, including bearings. Great supply of bearings. Okay, moving on. Let's have a look at the suspension system. These shocks, these are aluminum bodied shocks. These are standard shocks for RC vehicles. These are actually from a Duratrax Evader. These are the front shocks for a Duratrax Evader. For those of you not familiar with this type of stuff, these are oil-filled coilover shocks, meaning they have a spring, that's the coilover. The spring handles the rebound and the preload. There's a silicone oil in here. I don't know which weight is in these. These are just stock. The silicone oil is what provides the dampening. So when the shock gets pushed together, it's that oil in there. There's a plunger inside here with just a couple of small holes. And as that oil gets forced through the holes, that's what allows the dampening. It's not the spring. The spring is what causes it to rebound. The collar on here is actually a threaded collar, and you can change this, and that will change your preload, which changes your ride height. So for there, you can see how much distance, but if I preload it all the way down, you'll see it actually lifts up a bit. They come with the yellow springs. I decided to go with the green springs. The green springs are firmer, and I think that's working out. These are kind of soft. So that's what the shock system is. And if we have a look at the arms and the trucks, the arms look like this. So they're cut out on the bottom. That way it allows the full range of motion. I hope you can see that. That's why they can go up so far like that. It's because they're cut out like that. This is an earlier version. I realized that this wasn't going to work and that I had to have room in there, because when this drives over something, it needs to be able to go up in the middle, and this wasn't going to work. So the shock mounts right inside there, through with a screw. Up on here, once again, I'm back to my metal shafts. If you can see, I don't know if you can see, but there's a big hole on this side and a tiny little hole there. These are for what are known as Dubrow wheel collars. Come here. That's what these things are. They're a 3mm wheel collar. It's just a steel, round piece of steel with a 3mm hole and a tiny little set screw. I hope you can see the set screw in there. So these get pushed into this hole with the set screw up. Just like that. Well, ish. They get pushed in there. And then I can get my Allen key into that hole, back off the set screw. This is my bag of my box of prototype parts. So this is one of these blocks up here. Actually, this block up here. So you put that in there. Push the, I use round rods actually, not the hex rods. The rod goes in all the way through. You know, it'll be cut so it's the right length. And then I can come back here, put my Allen key in and tighten up that set screw, and those are set. And you can kind of see, if you're looking, you can see the shaft there. The rest of these are held together with screws. It's just that this is so wide. 3mm screws get really expensive when they get that long. Past 35mm, they tend to jump up in price a ridiculous amount. So using the shaft collars, plus it looks good, and I think it works very well. These, as you can see on the side, they also have those 3mm holes. These ones are made a little bit differently. That center hole is actually a lot bigger. So what do you think goes in there? If you said another bearing, you're right. So these get a bearing pressed into them, just like that, one on each side. The axles are actually the hex-shaped shafts. This one's bent. Don't ask. So I will actually use a 3mm die and tap and cut threads into the end of this. Push it through, put the wheel on, put a washer and a lock nut on there, going to measure where I need to be on the other side, cut it, cut threads on, and then screw it on. So these aren't screws. These are actually, they start off as these hex shafts, these steel hex shafts, and then I just cut the threads onto them. It works really easily. It's not hard to do, cutting threads, but that's how all these axles are made. And then everything runs on bearings. So I keep talking about bearings, lots of bearings. Once both tracks are done with all three sets, there's going to be a total of, 12, 24, 36 3mm bearings. 36 of these bearings throughout the whole thing, and 8 of the big bearings. There's 8 of these in the 4 in each track and 4 in each truck, so that's 12 with the 3 trucks. Each one of these gears has 2 bearings in it, so that's 2, 4, 6, 8. Oh, 8. So 8, 16 plus 24. Oh, so that's 40 bearings. Oh, I miscounted earlier. So I've actually got 40 of those 3mm bearings all throughout this. It's a lot of bearings. That's why this thing runs so smoothly, though. I just got to figure out how to do it, the noise. Okay, so this spine on here, this is the standard FL 505, basically a 1/2-inch fiberglass tube. The gearbox is also made with fiberglass tubes. These 2 tubes, I'm not going to do it with this one. I'm going to remake this so it stops. These 2 tubes, though, are going to be the main frame, and they're going to go all the way across to the other side, to the other track, and that's what connects the 2 tracks. I still have to make a new mount here. I'm I need to figure all this out, but there'll be another tube that comes off of here and goes to the other track, and then there'll be those 3 tubes that connect the side. So the whole middle of this, between the tracks, is free open space for me to do what I want to do. And boy, there's some interesting things I want to do. Okay, so let's direct our attention to the front of the vehicle now and have a look at the automated track tensioning system, also known as a spring on a stick. So right now I'm using these springs. I'm not sure if they're going to be too firm or if they're too soft yet. I won't know for sure until I've built the final full design, but this is it. So if we can see here, there's actually 2 fiberglass tubes. This is the main spine that goes all the way through, and then this one just pokes into the hole here. And I actually put the spring on the wrong one. I just realized that the spring is supposed to be on the bottom one. If we have a look at the prototype, I just had it out. There it is. So the idler block does not look like that. I can't show you what the idler block looks like because the only prototype I have is in there. But it's a block, and it has 2 recessed holes on each side for the big bearings. These are made similar to the way I was describing these, in that it has a center hex, a torque hex with the collar on it that fits in the bearing, but I'm not drilling through and using any steel pins because they don't have to drive each other. What I am using on the front is a 1/2 inch all thread with 1/2 inch lock nuts. Just this, it's your basic all thread ready rod with lock nuts on each side. The reason why I did that, there's 2 reasons why I chose to do it that way. Man, I got stuff falling all over. One, I don't have a lot of the 414 tube left anymore, and I need to make sure that I have enough for the next side and for the insides of here. Also, I needed to add some extra weight on the front. So I've got the motor way at the back, and that might have been a mistake because it's put all of the weight right on the back, way out here. So I had to counterbalance it a little bit, and the extra weight from the 1/2 inch nuts and whatnot put some good weight on there. And I don't think this is going to be much of a problem once I build the middle section, because I'll have the battery up front and I'll put some other components and that'll counterbalance it back. So as I was saying about the spring on a stick, so they got the 2 tubes here. Oh, before I go too far, let's talk about wheels. Almost forgot. These are cool. So the wheels all have Ninja Flex tires on them. The gear, also the drive gear, also has a Ninja Flex tire on it. On the drive gear, this Ninja Flex tire is actually epoxied on. I did that just by spreading epoxy all over the teeth, put the Ninja Flex tire on, and then I hooked rubber bands across to hold it all in place. For these ones, and for the idler gears, I don't need to do that because I can just pop these off. If you can see, there's actually a groove down the center of the tire. And if we look on the inside of the Ninja Flex, I hope you can see that, there is a protrusion on the inside of the Ninja Flex, on the inside of that tire. So that groove, that protrusion on the tire just snaps right inside that groove and locks the tire on. And they're not coming off unless I want them to come off. See, just like that. And now it's locked right on there. The idler works the same. Okay, so on the inside of the idler block is 2 smaller holes for 414 tube. The 414 tube is sanded and the inside of the 505 is filed so that they run inside each other really, really nicely. The final design will actually have grease on that, and then I'll make some boots out of, it's called TPE 80A. Well, the shore hardness is 80A. It's a lot softer, more flexible than Ninja Flex. So I'm actually going to make boots to cover these with because there's going to be grease in there and I want to keep the dirt out. So the spring, this is what I've called floating idlers. There's not hard connected. So everything else is bolted together. But this has two, like I said, the two 414 tubes. That'll be crazy glued. Well, actually a thick CA glue will glue those smaller tubes into the block. And then those tubes just slide right inside these bigger tubes. So this spring that's there, if we can see it, I can move this back and forth. And you see how that spring just keeps the right amount of tension. As soon as I let go, it just pushes it back. So when the suspension on the bottom releases, that spring pushes the idler block out. It doesn't have a lot of travel. It doesn't need a lot of travel. But that spring pushes the idler block back out, keeps the proper tension on the track at all times, irregardless of where the suspension is, or how much compression there is, or if it lifts off the ground, the suspension is strong enough to overcome this spring and can push out, and this will come back in. And that's how it works. That's all it is. It's not coming off because these tubes are actually really long. They come all the way into here. I'm not using them right now. I've actually only got a piece of dowel and a piece of 3D printed one of these just stuck in there right now. So there is a bit of play. If I can twist it, you can see that it does twist, but that's only because I'm using a small dowel and this. They don't fit very well. Once I'm using the right tubes, that's not moving, except in and out. It will not twist. It'll be a solid connection. Because these tubes are not flexible. At this length, they won't bend. You put them on a 15-foot kite, they flex a huge amount, but that's over 15 feet. Over 10 centimeters, the bend is hardly noticeable. It takes massive force to actually bend that, so it's going to be awesome. But that's the automatic tensioning system. These springs, these copper springs, well, I got one right here. These are the extra firm springs. So depending on exactly what I want to do, I can put two of these in there. Or I could go to softer springs, or a medium spring, or a super soft spring, and put two springs on the same one. So I have a lot of options to play with to determine exactly how much force I'm going to actually need on that. So that's my track. This is probably a long video. Sorry, but there was a lot to talk about. I have more to talk about. I almost forgot. So in my previous video, I talked about using Ninja Flex for these track pads. I've since changed my mind. These are now TPE. Ninja Flex is very soft. It's soft. It's not as soft as the TPE, but it's soft and it's nice and grippy. The TPE is a little harder, a little stiffer, and not as grippy. But it also has a much higher wear ability. So they're not going to wear out as fast as Ninja Flex, and they're not as grippy, which is actually a good thing. I was always a little worried that having this much Ninja Flex across the entire track, Ninja Flex in each one of these was going to be a lot of grip. And on a track system, you don't want a lot of grip, because when you get onto some surfaces, it'll be hard to turn. If these things are just gripping the ground like Spider-Man's fingers, the tank won't turn very well. So by using these pads, they're less grippy. They wear a lot longer. I think it's going to be a lot better because there's so much contact with the ground. Remember, this is only 2/3 of it. There's another, lot to come. So these pads are going to work very well. They serve for grip. They serve to quiet the tank across the ground. I don't know why I'm worried about that. If I didn't use any Ninja Flex, you still wouldn't hear it over top of the gears. I really need to figure out how to quiet those gears. So yeah, these are TPE track pads, Ninja Flex tires. The idlers, I'm using TPE 80A just because I just bought a roll of that and I wanted to check it out. So I figured I'd use it on this. It's grippier than this, so I'm just going to go ahead and use it. I haven't quite figured out the best way to print it. This has an odd indentation in the middle, which I don't understand. So that's it. All of the gray, most of the gray, is printed in PLA Plus from eSun. It's PLA Plus material. Some of this is ABS, like the nuts are ABS, the washers are ABS. This gear is ABS. I don't know why I did that in ABS, but I just ended up doing it in ABS. Everything else is, some of this is actually standard PLA, like these up here, these blocks, and the rollers are standard PLA. When I remake this, this will be standard PLA. The wheels are currently PLA plus, and I'm going to keep them that way. The trucks are PLA plus. I think that covers it. Yep. So there we go. There's my big ass track system. So the next step is just to print out the next. I'm going to reprint these pieces into the final, reprint the new truck. And then print a whole new suspension system. So a new truck, a new arm, 4 wheels, the suspension block, the main arm block. Then I gotta cut myself a new piece of fiberglass for the new spine, more shoes, put it all back together, and then I'll have the full size. And that'll be my next video, just to show off how big this thing's gonna be. I am very happy with the way this ran. I don't see a need to change anything. My floating idler works for the tension system. The shocks and the trucks and the whole shock system works great. I'm just going to plow ahead and start doing it. I've also got a lot of these track pads to print and glue. And I got really lucky. Canadian Tire was having a sale on clamps. Package of 2 clamps for $7. Normally, what were they, like $17? They were on sale for like 60% off. So I bought a whole bunch. So that's going to help me get all of these glued and clamped a lot quicker. So yeah, good deal. Good timing on that. So I got lots of clamps now, no problem. So yeah, my schedule, the way I'm going to do this is when I get home from work, I will print out a crap load of track pads. And then before I go to bed at night, I'll start another print for either, like 6 shoes or one of these. And then the next night, the first thing I'll do is I'll start printing more track pads. I'll glue the track pads. While those are printing, I'll glue the previous day's track pads to the shoes and then sort of do an assembly line like that. It's probably going to take a couple of weeks to get everything else printed out. It takes longer to print this stuff than I had originally anticipated. If I do 4 shoes at a time, that's 5 hours and 50 minutes to print them. Oh, excuse me. 20% infill, 3 perimeters, 3 surface layers. Basically, all of this is printed with those same settings. So yeah, that's it. I think I'm done now. I am done. Oh, I'm not done. There's another block, one of these shafts that goes from here to here. The reason why is right now, this spine is only supported by these 2 blocks. So all of the pressures of the on the track system are going to get transmitted through these 2 blocks and this 1 block. So I decided to add a more direct one. So this shaft goes in here, but then it comes out way up top. So when it's turning, it's trying to twist all this. Now there's a lot going on here, so it's probably good enough, but I decided to put one more in that's in line. It's coming straight off the side. So that force is going to be transferred better into this block. Overall, I think that's actually a really good idea. It still gives me all the clearance I need inside. So, okay. I think that was definitely the last thing I needed to say. All right. Well, thanks for watching. I'll be posting the next video on this in a couple of weeks once I've got the full size done. And then once that's done, the next step is to print the right track. And I don't think I'm actually going to have all of that done this year. It's probably going to take me at least until sometime into the new year, into January, to get all of that done. There is a lot of printing that has to do. One other thing I'll show you, if I knew where they are, is these things. These are jigs. So in order to get these spaced properly, and it's very important that these are all square to each other. They can't have any twisting in them, because any twisting would be reflected down into these trucks and into the tire, into the wheels, and that could cause binding. So it's very important that everything is perfectly square and lined up. So I made these jigs. It doesn't work when they're already on here. But in order to line everything up, this comes off, I lay it on the table, and this pops right into here, and it gives me the perfect spacing between here, and this lines up onto the top, this is on the side, this is on there, so it gets them nice and square. This one is for the next section. It pops right into here, lines these up with this block for me. You can see how that works. This is the third one. Goes on like this. It also lines up these blocks here. That's what this is. If I pop that onto there, you can see that this lines up with the edge of that. Sorry, that side right there. And then it lines up on this block, and then I can drill the holes from the other side as it's laid on the table. So yeah, the only way to make sure these are all lined up perfectly with the perfect spacing, perfect squareness, was to make some drill jigs for them. And that's what these are. Okay, now I'm done. So leave a comment. Tell me what you think of my track system. One more thing. I tried to do a bit of math. Earlier on I was saying, see if you can figure out how fast it was going. So my math came out to 2.4 meters per second. Not as fast as I thought. So I might have more incentive to change the gear ratio, but I don't know. You know what? It's a tank. It's not supposed to be all that fast. So I don't know. I'm just going to go with it. The other dilemma I'm having now that I started looking at this is maybe 3 suspensions isn't enough. Maybe I should make it longer and go with 4 trucks and 4 suspensions each. That's huge. But considering what I'm going to be putting inside this thing, oh man, it's not going to be disappointing, that's for sure. It's going to be cool. It's going to be cool. Okay, so once again, thanks for watching. Subscribe, comment, tell me what you think. You can also tell me that I talk too much. Okay, bye now.